Hello and welcome to the second round of the RAGOps framework evaluation. My name is Sofia Konchikova, and today I will walk you through the implementation of the RAGOps framework. If you haven't seen the first video where I introduced the theoretical foundation, you can find the link in the video description below. In the first evaluation, we assessed the theoretical foundation of the RAGOps framework, where we defined four key pillars: data management, model management, prompt management, and system management. Our research follows the design science research methodology, which emphasizes iterative development and continuous evaluation of design artifacts. This presentation marks the second evaluation cycle following the initial refinement of the framework. In this second evaluation, we validate our RAG system architecture, review DevOps and MLOps integration into RAGOps, including CI/CD and monitoring, and assess whether prompt versioning and automated testing support a scalable production-grade setup. As an example, we present the Huber chatbot for Humboldt University's economic faculty, and your feedback is essential to refine the framework. This diagram shows the main stages of our RAG system architecture. So we see how we get the user question, it lands into our hybrid retriever where it fetches candidate documents from both a vector store and a BM25 index. Then we have a re-ranker to refine the relevance. The selected documents go into the generation layer where the generator produces the final answer. So it looks easy. It sounds also not extremely complicated, but though we will go into the details of each step. And we start with a data management pipeline. So we defined three key requirements. It's automated orchestration to minimize manual work, scalability to handle growing data, and user demand. Also, comprehensive monitoring of both pipeline performance and the data quality. It looks difficult. The data management pipeline, though, consists of four key components: data acquisition and content extraction, then data enrichment, data vectorization, and database versioning. So we also use external services like PostgreSQL, GitHub, OpenAI. And though it may seem complex initially, we will delve deeper into the system implementation step by step. The initial stage of our data pipeline is data acquisition, which automatically ingests raw content from the faculty website and maintain data quality. A GitHub action triggers two phases. The first one is a sitemap processing with the sitemap script, which parses URLs, updates the page raw table, and flags inactive links. Content extraction, where HTML is fetched cleaned using Trifilateral, and then it is stored in the page content. These are two main steps. Then the content enrichment pipeline automates processes, ensures data quality, and includes monitoring. It's triggered by GitHub action, the script called check data. It identifies pages needing update. For keywords, we have keyword processor script that handles lemmatization and normalization, while embedding processor creates vector representation for semantic search. And this method promotes efficient processing with traceability and minimal redundancy. Then we have data vectorization. This step involves converting clean text into high quality vector embedding for efficient semantic search. And the process includes fetching content from the database, using chunk utils to split text into configurable chunks for flexibility, generating vector representations by calling one of the models. It can be an OpenAI model, it can be a self hosted Llama, and others. Both text chunks are embedding are stored in the page embeddings table. And as the success of the semantic search relies on a careful selection and versioning of embedding models, we also support experimentation and usage of different embedding models. The final step of the data pipeline is vector database maintenance, ensuring outdated or irrelevant data is being removed. We have garbage collector script that queries the page raw table for inactive URLs and deletes related records from page content, page keywords, and page embeddings. Then we have a scheduled GitHub action that automates this garbage collection step. And to close the data architecture section, we have two cross-cutting concerns. And first one is a monitoring. Each sitemap and data processing run logs metrics into historical record, helping track changes, spot anomalies, and quickly resolve any issues. And we have database versioning that is achieved by using Alembic. We also use some Boolean is active flag, and together with the garbage collector, it ensures that only current and valid data is processed. These measures provide a reproducible and auditable data environment. Next in the queue is a model management pipeline. And this slide outlines the model management architecture, very general, including configuration, retriever and generator components, embedding support, and the evaluation framework. The next slides will detail each area, starting with the configuration. And well, let's explore it. So we have retriever management, and we see this module in three layers. The first one is a configuration that defines key settings, embedding models, chunking strategy, hybrid weighting, and re-ranking. Then we have embedding support, a unified embedding generator that switches between OpenAI and Hugging Face without changing core logic. We have a core retriever that combines dense vector search and sparse BM25 search, blends cores, and optionally re-ranks with the cross encoder. And this modular setup enables flexible tuning and experimentation and independent optimization of each component while keeping the architecture clean and scalable. Well, now we cover the generator management, and it produces final response from the retrieved context. The system supports flexible model integration. As I said, we can use local models such as Llama, hosted APIs like OpenAI API, and together enabling easy switching between open source and commercial providers. The pipeline starts with the prompt factory, constructing structured prompts from user queries and retrieved context. Then we have configurable parameters such as temperature, token limits, and stop sequences. This all controls response generation. And we want to ensure that this setup is repeatable, traceable. And now talking about evaluation, another part of model management, which is extremely crucial. We discussed already in the previous presentation how we create the custom question answering data sets. And here we use them, we generate them via, again, LLM sampling. We calculate metrics like MRR, heated K, and we log results to weights and biases for the further experiment tracking. The generator evaluation combines traditional metrics like Rouge, cosine similarity, with LLM-based metrics as AI as a judge to assess clarity, factuality, and relevance. And together, this feeds into end-to-end testing, enabling data-driven optimization and continuous improvement across all layers of the system. So, to support flexible experimentation and robust performance, we built a dedicated data and configuration infrastructure. We have PostgreSQL that handles dense semantic retrieval, and together with TS, we use TS Vector for subparse search and custom functions. We also have Pydantic that manages environment-specific settings, while a table switching mechanism dynamically routes to different data sets or experiments without any code changes. And, well, now we can talk about more exciting stuff, which is a prompt management and something pretty novel for the RAGOps framework. So this is, again, the overall prompt management system architecture. And we have key components that include prompt factory that constructs base, medium, and advanced prompts from a shared template for consistency. We have reusable chat prompt builder that assembles this modular prompt. We have prompt strategy and weighted prompt strategy. We use it for composition and A/B testing. We have a prompt selector that can choose a prompt at a runtime, and we have a prompt manager that again tracks available templates. We have integration with lang views and weights and biases. So, the prompt management core is a modular version control system that separates prompt assembly logic from content. Prompt component is the smallest unit, for example, instruction or roles, each linked to versioned content in lang views. Prompt configuration defines which components form a template, and reusable chat prompt builder fetches and assembles them together. This works like a prompt template in engine and repository. The Langfuse prompt repository is shown here. It stores version prompt components, again, roles, instruction, question, context blocks. We use it for version tracking and rollbacks. Next are prompt templates and the factory pattern, which enables scalable and reusable prompt generation. At the core is the base prompt template, defining shared structure for implementations like base prompt, medium prompt, advanced prompt, each with its own prompt configuration recipe. The prompt factory creates this template through a single create prompt method, so client code can request a prompt type without knowing how it's built. And templates then are passed to reusable chat prompt builder, generating final prompt on the fly. And again, prompt management and selection. The prompt manager acts as a central registry, providing one access points to all prompt templates, ensuring consistency and easy management across the system. And prompt selector encapsulates the logic for choosing prompt based on the context. While currently simple, it's designed for future extension using query metadata, user roles, or past interactions. The evaluation system brings structure, traceability, and data driven insights into prompt development. At its core, we have 1DB evaluation, weights and biases evaluation, that handles template retrieval from prompt factory, evaluation, execution, and logging of performance metric to the 1DB, weights and biases. Metric calculations are separated into evaluation functions, making the system modular and future proof, allowing the new metrics to be added without modifying the evaluation engine. Last but not least, system management deployment, very important. And we see the full operational pipeline from development to deployment and monitoring. And so here we look at each layer. We have CI, CD layer, version layer, infrastructure layer, and we can look at it in depth. So first of all, CI/CD pipeline that automates the entire lifecycle of our RAG system from data acquisition to evaluation using GitHub Actions. It has three main pipelines: data pipeline that we discussed already. We have data processor and garbage collector. And we have application pipeline handles linting, testing, and deployment. Evaluation pipeline runs prompts and retriever evaluations to ensure updates maintain quality. And dependency management ensures components run only when they needed, keeping the pipeline event-driven, synchronized, and low maintenance. Monitoring layer enables a data-driven feedback loop, giving deep insights into the system health and component level performance. Again, we have data pipeline monitoring that we have GitHub action logs that provide transparency for each stage. We have retrieval and generation quality monitoring using weights and biases logs metrics. We have prompt application monitoring together with Langfuse, traces prompt execution, Sentry captures application error, and internal logs. So we want to have full observability. The versioning layer ensures repeatability, consistency, and traceability across the entire system, covering code, data, models, and infrastructure. We use a multi-artifact version control, not only source code, but also configs, CI/CD scripts, question answering dataset, and experiment outputs. They are all versioned via GitHub, weights and biases, Sentry. Infrastructure is managed as code. We have Docker Compose that keeps local environment consistent with production. We have Terraform that provides Hetzner cloud services, Hetzner or cloud services like PostgreSQL and application servers. We want to make rollback safe. And we also have robust multi-level testing and validation layer We have data level validation, that we have some script check data pi that automatically detects formatting issues, missing fields, schema mismatch before data reaches production. We have end-to-end testing, which is a manual UI test that validate full workflows, ensuring interfaces and interaction function correctly. We have retrieval evaluation, which benchmarks retrieval using information retrieval metrics. We have generator and prompt evaluation. We have 1DB evaluation, and all results logged to weights and biases, transforming evaluation into continuous CI integrated quality loop for every component. So the Huber toolset powers the RAGOps implementation end to end. We have Python, Spacey, LangChain for ingestion, chunking, tagging, and formatting. We have PostgreSQL that handles structured storage, SQL Alchemy, and Alembic for schema and migration management. We have Quadrant for vector search. We have GitHub Actions. We have also model components that support Llama CVP, OpenAI, and Together AI. For monitoring, we have landfills, weights and biases, and Sentry. Infrastructure uses Docker, Terraform. We have Flask and Hetzner for application and UI. So this is the live Huber interface for Humboldt University of Berlin, and this is the main page. Behind the simple UI is a robust, modular, and fully automated rack system, tying together prompt management, retrieval, evaluation, deployment, and monitoring all in one product. This is the find sources interface. In Huber, users enter a topic here, for example, information system, and receive semantically relevant links. Chat support chat capabilities, so you can chat with it. What's more important, we have another configuration panel that allows live adjustments to the retrieval pipeline. Users can switch embedded models, select a ranker, and tune the hybrid search. Um, so we also have name entity recognition filtering, and changes are saved directly to the environment file, ensuring version consistency. And this allows us rapid experimentation. The evaluation dashboard centralizes retriever and generator performance testing across prompt setups, as it discussed, but now it's also available through UI. And we have comprehensive analytics dashboard for admin users that gives real-time visibility into Huber's production performance. We have total requests, unique queries for usage, average response time for speed, and mean reciprocal rank for retrieval quality. So thank you for your attention. I greatly appreciate your feedback through the questionnaire. For any questions or follow-up, feel free to contact me via email or LinkedIn. Your input is always invaluable for refining the RAGOps framework.